In this last video, we will talk about using the substitution property to evaluate definite integrals. And the idea is going to be exactly the same to get started, except for the fact that we're going to have limits of integration to worry about. So seeing an integrand of this form, g of x inside a function, its derivative outside, this function derivative pair, we think we can use the substitution u equals g of x. So if u is equal to g of x, du, once again, would be g prime dx. And in our original integral, our limits of integration are going from x equals a to x equals b. So what we need to do is think about changing those limits of integration. So for the lower limit of integration, we think x is equal to a. And if we look at our substitution, if we want to go from x to u, when x is a, u is g of a. And that gives us our lower limit of integration in the rightmost integral. Similarly, for that upper limit, when x is b, the substitution gives us that u is g of b. And that gives us our upper limit of integration. Now notice, once again, we go from all x's to all u's. And all u's includes changing around our limits of integration. But the nice thing is that these two definite integrals are equivalent. So once we've changed our limits of integration, we can just concentrate on the new integral. We evaluate it, we get back a number, that is our solution. So let's try this out. So in the integral given to us, we see that, yeah, you could simplify, but you'd have to have quite a bit of patience for 1 plus x squared to the 10th. So instead, let's try a u substitution. And I say try because there's never a guarantee. So if we let u be 1 plus x squared, then du would be its derivative, so 2x dx. So the 2x dx we have is our du, so it works very conveniently. So in terms of getting everything in terms of u's, we have a definite integral whose limits of integration we need to determine, u to the 10th du. So this becomes significantly easier, but we do need to change our limits of integration because recall, this integral we started with goes from x equals 0 to x equals 1. So when x is equal to 0, looking at our substitution, our lower limit of integration when x is 0 is going to be u equals 1 plus 0 squared. So u equals 1. For our upper limit of integration, when x is 1, u is going to be 1 plus 1 squared, which is 2. So our limits of integration are going from 1 to 2. And as mentioned, once we change around those limits of integration, this new definite integral that we have in terms of u is all we need to be concerned about. We can evaluate that, get back a number, it is our solution. With a definite integral and a u substitution, we change our limits of integration, and we do not need to resubstitute. So using the fundamental theorem of calculus, antiderivative 1 over 11, u to the 11, we plug in a 2, we put a minus sign, we plug in 1. So one last example using a substitution with a definite integral. So once again, when you see something of this form, in terms of previous approaches comparing to common formulas, there's really nothing we can do. We have no rule of anti-differentiation or integration that allows us to break it up over a fraction. So our only choice here is hopefully we're going to be able to do a substitution. And what we want to do is pick u to be something inside another function. So the most inside we could be is inside this square in the denominator. So what does that give us? So no guarantees here, but we're going to try. U equals x squared plus 2x plus 6. Du is 2x plus 2 dx. And what we need to do is somehow take this 2x plus 2 dx And that's going to allow us to get this dx term in terms of du. Now in our integral, what we have is x plus 1 dx. So in terms of that x plus 1 dx, we can definitely get that over here just by dividing by a 2. So we could write this as 1/2 du is x plus 1 dx. So this becomes 1/2 du. So we can now get our integrand solely in terms of u's, which is our goal. You have 1/2, which is a constant that pulls out front, so that 1/2 is coming from there, multiplied by the integral of 1 over u squared du. But we do need to switch our limits of integration. So in terms of our lower limit, when x is 0, u is equal to 0 squared plus 2 times 0 plus 6. For our upper limit of integration, when x is 1, u is equal to 1 squared plus 2 times 1 plus 6. So we're going from u equals 6 to u equals 9. And this puts everything solely in terms of u. So once we are able to evaluate using the fundamental theorem of calculus this resulting integral, that number is going to be our solution. So 1 over u squared, note, is really u to the minus 2. Minus 2 plus 1 is minus 1. So we have 1/2 times 1 over minus 1 u to the minus 1 from 6 to 9. So we can say this is minus 1/2 1 over u from 6 to 9. So we're going to let the minus 1/2 hang around up front, plug in 9, minus sign, plug in 6. And if we simplify this just a bit by combining terms, common denominator 36, we end up with 1 over 36. So as a reminder, if you are evaluating a definite integral with a u substitution, you need to change your limits of integration, but as an upside, when you do change those limits of integration, you keep it in u for the remainder of the problem.